Cloud and Data Metamorphosis is a multi-video series. In the larger video series, entitled AI, ML, and Advanced Analytics on AWS. This is part 3 of video 3, which is a continuation of the first and second videos in Cloud and Data Metamorphosis. Let's quickly overview what we just learned in part 2 of Cloud and Data Metamorphosis and quickly introduce you to the topics in this part 3 of Cloud and Data Metamorphosis. In part 2, I covered the following: amazing data factoids that impact analytical systems, analytical platform evolution, dark data, the problems with data silos, data architecture evolution, and modern distributed data pipelines. In part 3, I'll cover serverless architectures, AWS Lambda, AWS's Serverless Application Model, or SAM, all about AWS's containers, AWS Fargate, and Amazon Elastic Container Registry, or ECR. Let's now look at the evolution of cloud services in regard to serverless architectures. It wasn't that long ago that all companies had to buy servers, guessing how many they'd need for peak usage. What normally happened was they took the side of being prepared for the worst and ended up over-provisioning the amount of servers, costing a ton of money up front. In the image on the right, with AWS Serverless, gone are the days of racking and stacking, called undifferentiated heavy lifting in AWS terminology. It has a pay-as-you-go pricing model, dramatically reducing costs, and thus a perfect way to experiment and innovate cheaply. It has the proper data pipeline architecture of decoupling storage from compute and analyze. AWS Serverless also provides load balancing, auto-scaling, failure recovery, security isolation, operating system management, and utilization management are all handled for you. Serverless means greater agility, less overhead, which basically means setting up and maintaining servers, better focus, increased scalability, more flexibility, and faster time to market. Serverless computing came into being back in 2014 at the AWS reInvent annual conference with Amazon Web Services' announcement of AWS Lambda. AWS Lambda is an event-driven serverless computing platform provided by AWS. Serverless is a computing service that runs code in response to events that automatically manages the computing resources required by that code. Serverless computing is an extension of microservices. The serverless architecture is divided into specific core components. To compare microservices and serverless components, microservices group similar functionalities into one service, while serverless computing defines functionalities into finer-grained components. The code you run on AWS Lambda is called a Lambda function. After you create your Lambda function, it's always ready to run as soon as it's triggered. Lambda functions are stateless, with no affinity to the underlying infrastructure, so that Lambda can rapidly launch as many copies of the function as needed to scale to the rate of incoming events. With AWS Lambda, you pay only for the requests served and the compute time required to run your code. Billing is metered in increments of 100 milliseconds, making it cost-effective and easy to scale automatically from a few requests per day to thousands per second. Since AWS Lambda's release, there's been an astonishing growth of over 300% year over year of use. Serverless analytics can be done via Amazon Athena, which we'll get into more detail about later. Athena makes it easy to analyze big data directly in S3 using standard SQL. How it works is that developers create custom code, then the code is executed as autonomous and isolated functions that run in stateless compute services called containers. Let's back up a bit here and discuss common AWS Lambda use cases. These include static websites and complex web applications, back-end systems for apps, services, mobile, and IoT, data processing for either batch or real-time streaming computing using MapReduce. It can power chatbot logic. It can power Amazon Alexa's voice-enabled apps, and for implementing the Alexa skills set. IT automation for policy engines is another use case, extending AWS services and infrastructure management. The architectural diagram on this slide is one way to create a simple website using all serverless AWS services. Each service is fully managed and doesn't require you to provision or manage servers. The only thing you need to do to build this is to configure them together and upload your application code to AWS Lambda. The workflow represented in this diagram goes like this. Highlighted by the number 1 in a blue circle is the first step, where you configure an Amazon S3 bucket to host JavaScript, CSS, HTML, images, and other typical website assets. After uploading your assets to the S3 bucket, you need to ensure that your bucket has public access settings. To do that, in the S3 Permissions tab for the bucket, there's a tab located within the Permissions tab named Properties, and that's where you enable static website hosting. This will make your objects available at the AWS region-specific website endpoint of the bucket. Your end users will access your site using the public website URL exposed by Amazon S3. When users visit your website, they'll first register a new user account. This is done by Amazon Cognito, highlighted by the number 2 in a blue circle. After users submit their registration, Cognito will send a confirmation email with a verification code to the email address of the new visitor to your site. The user will return to your site and enter their email address and the verification code they received. After users have a confirmed account, they'll be able to sign in. When a user signs in, they enter their username or email and password, which triggers a JavaScript function that communicates with Amazon Cognito and authenticates using the Secure Remote Password Protocol, or SRP, and receives back a set of JSON Web Tokens, or JWT. The JWTs contain claims about the identity of the user and will be used later to authenticate against the RESTful API of the Amazon API Gateway. Cognito user pools add sign-up and sign-in functionality to your application. A user pool is a user directory in Cognito. With a user pool, your users can sign into your web or mobile app through Cognito. Next, you create a backend process for handling requests for your app using AWS Lambda and DynamoDB, highlighted by the number 3 in a blue circle. The Lambda function runs its code in response to events, like HTTP events. Each time a user makes a request to the static website, the function records the request in a DynamoDB table, then responds to the front-end app with details about the data being dispatched. The Lambda function is invoked from the browser using Amazon API Gateway, highlighted by a number 4 in a blue circle, which handles all the tasks involved in accepting and processing up to hundreds of thousands of concurrent API calls, including traffic management, authorization and access control, monitoring, and API version management. API Gateway acts as a front door for applications to access data, business logic, or functionality from your backend services, such as workloads running on Amazon EC2, code running on AWS Lambda, and any web application or real-time communication applications. The API Gateway creates a RESTful API that exposes an HTTP endpoint. The API Gateway uses the JWT tokens returned by Cognito user pools to authenticate API calls. Then you connect the Lambda function to that API in order to create a fully functional backend for your web application. Now, whenever a user makes a dynamic API call, every AWS service is configured properly and will run without you having to provision, scale, and manage any servers. AWS has an open source framework for building serverless applications called the AWS Serverless Application Model, or SAM. It provides shorthand syntax to express functions, APIs, databases, and event source mappings. With just a few lines per resource, you can define the application you want and model it using YAML. During deployment, SAM transforms and expands the SAM syntax into CloudFormation syntax, enabling you to build serverless applications faster. If you watched any of the demos from the Pluralsight course, and I hope you did, you'll be familiar with how cool CloudFormation is. Delivering a production serverless application that can run at scale demands a platform with a broad set of capabilities. AWS supports enterprise-grade serverless applications in the following ways. There's a cloud logic layer, which empowers your business logic with AWS Lambda, which can act as the control plane and logic layer for all your interconnected infrastructure resources and web APIs. It allows you to define, orchestrate, and run production-grade containerized applications and microservices without needing to manage any infrastructure when using AWS Fargate, which I'll get into soon. Serverless platforms have responsive data sources. You choose from a broad set of data sources and providers that you can use to process data or trigger events in real time. AWS Lambda integrates with other AWS services to invoke functions. A small sampling of the other services includes Kinesis, DynamoDB, Cognito, as we just saw, various artificial intelligence services, queues and messaging, and DevOps code services. It has an integrations library. The AWS Serverless Application Repository is a managed repository for serverless applications. It enables teams, organizations, and individual developers to store and share reusable applications and easily assemble and deploy serverless architectures in powerful new ways. Using the Serverless Application Repository, you don't need to clone, build, package, or publish source code to AWS before deploying it. Instead, you can use pre-built applications from the Serverless Application Repository in your serverless architectures, helping you and your teams reduce duplicated work, ensure organizational best practices, and get to market faster. Samples of the types of applications that you'll find in the application repository include use cases for web and mobile backends, chatbots, IoT, Alexa skills, data processing, stream processing, and more. You can also find integrations with popular third-party services like Slack, Algorithmia, Twilio, Loggly, Splunk, Sumo Logic, Box, and many, many more. There's a developer ecosystem for serverless applications. AWS provides tools and services that aid developers in the serverless application development process. AWS and its partner ecosystem offer tools for continuous integration and delivery, testing, deployments, monitoring and diagnostics, SDKs, frameworks, and integrated development environment, or IDE, plugins. Insofar as application modeling frameworks are concerned, that's AWS SAM. There's also orchestration and state management. You coordinate and manage the state of each distributed component or microservice of your serverless application using AWS step functions. Step functions make it easy to coordinate the components of distributed applications and microservices using visual workflows. Building applications from individual components that each perform a discrete function lets you scale and change applications quickly. You also get global scale and reach. You can take your application and services global in minutes using AWS's global reach. AWS Lambda is available in multiple AWS regions and in all AWS Edge locations via Lambda at the Edge. You can also run Lambda functions on local connected devices with AWS Greengrass. For reliability and performance, AWS provides highly available, scalable, low-cost services that deliver performance at enterprise scale. AWS Lambda reliably executes your business logic with built-in features such as dead letter queues and automatic retries. For security and access control, you enforce compliance and secure your entire IT environment with logging, change tracking, access controls, and encryption. You can securely control access to your AWS resources with AWS Identity and Access Management, or IAM. You manage and authenticate users of your serverless applications with Amazon Cognito. You use Amazon Virtual Private Clouds, or VPC, to create private virtual networks which only you can access. With the AWS serverless platform, cloud developers and architects can focus on the analytics and not the infrastructure or undifferentiated heavy lifting, and you only pay for what you use. I'll show you 3 simplified use cases that use serverless architectures. The first sample is a real-time streaming data pipeline. In the diagram, data is published to an Amazon Kinesis data stream. The AWS Lambda function is mapped to the data stream and polls the data stream for records at a base rate of once per second. When new records are in the stream, it invokes the Lambda function synchronously with an event that contains stream records. Lambda reads records in batches and invokes your function to process records from the batch. The data collected is available in milliseconds to enable real-time analytics use cases such as real-time dashboards, real-time anomaly detection, dynamic pricing, and more. The next sample shows creating a chatbot with Amazon Lex. Amazon Lex is used to build a conversational interface for any application using voice and text. Amazon Lex provides the advanced deep learning functionalities of automatic speech recognition, or ASR, for converting speech to text, and natural language understanding, or NLU, to recognize the intent of the text, to enable you to build applications with highly engaging user experiences and lifelike conversational interactions, enabling you to build sophisticated natural language conversational bots or chatbots. To build an Amazon Lex bot, you will need to identify a set of actions known as intents that you want your bot to fulfill. A bot can have multiple intents. For example, a book tickets bot can have intents to make reservations, cancel reservations, and review reservations. An intent performs an action in response to natural language user input. To create a bot, you will first define the actions performed by the bot. These actions are the intents that need to be fulfilled by the bot. For each intent, you will add sample utterances and slots. Utterances are phrases that invoke the intent. Slots are input data required to fulfill the intent. Lastly, you will provide the business logic necessary to execute the action. An action is fulfilled via integration with AWS Lambda for fulfillment of the action or business logic. Amazon Lex integrates with AWS Lambda, which you can use to easily trigger functions for execution of your back-end business logic for the data retrieval and updates. This last sample shows using Amazon CloudWatch events to respond to state changes in your AWS resources. In this diagram, Amazon CloudWatch events help you respond to state changes in your AWS resources. When your resources change state, they automatically send events to an event stream. You can create rules that match selected events in the stream and route them to your AWS Lambda function to take action. However, a Lambda function can be created to direct AWS Lambda to execute it on a regular schedule. You can specify a fixed rate, for example, execute a Lambda function every hour or every 15 minutes, or you can specify a cron expression. In an earlier slide, I mentioned that serverless Lambda functions are executed as autonomous and isolated functions that run in stateless compute services called containers. Let's look at containers and the value they provide in more depth. AWS Lambda functions execute in a container, also known as a sandbox, that isolates them from other functions and provides resources, such as memory, specified in the function's configuration. So what's the difference between virtual machines and containers? Virtual machines and containers differ in several ways, but the primary difference is that containers provide a way to virtualize an operating system so that multiple workloads can run on a single operating system instance. With virtual machines, the hardware is being virtualized to run multiple operating system instances. So how is a Docker container different from a hypervisor? Docker containers are executed with the Docker engine rather than the hypervisor. Containers are therefore smaller than virtual machines and enable faster startup with better performance, less isolation, and greater compatibility possible due to sharing of the host's kernel. Virtualization offers the ability to emulate hardware to run multiple operating systems on a single computer. So what's the difference between hypervisors and containers? In terms of hypervisor categories, bare metal refers to a hypervisor running directly on the hardware, as opposed to a hosted hypervisor that runs within the operating system. When hypervisors run at bare metal level, it controls the execution at the processor. From that perspective, operating systems are the apps running on the hypervisor. So from a Docker perspective, containers are the apps running on your operating system. Virtualization means it removes the need to directly manage something. Similar to how a virtual machine virtualizes server hardware, containers virtualize the operating system of a server. In the beginning, the only option available as a launch type for containers was Amazon EC2. Soon, customers started containerizing applications within EC2 instances using Docker. Containers made it easy to build and scale cloud-native applications. The advantage of doing this was that the Docker images were packaged application code that's portable, reproducible, and immutable. Like any new application solution, once one problem is tackled, another one eventually is identified. This is how advancements in technology are born. A customer has a new request, and companies discover ways to fulfill that request. The next request was that customers needed an easier way to manage large clusters of instances and containers. The problem was solved by AWS creating Amazon Elastic Container Service, or ECS, that provides cluster management as a hosted service. It's a highly scalable, high-performance container orchestration service that supports Docker containers and allows you to easily run and scale containerized applications on AWS. Amazon ECS eliminates the need for you to install and operate your own container orchestration software, manage and scale a cluster of virtual machines, or schedule containers on those virtual machines. However, cluster management is only half the equation. Using Amazon EC2 as the container launch type, you end up managing more than just the containers. ECS is responsible for managing the lifecycle and placement of tasks. Tasks are 1 to 2 containers that work together for a common goal. You can start or stop a task with ECS, and it stores your intent. But it doesn't run or execute your containers. It only manages tasks. An EC2 container instance is simply an EC2 instance that runs the ECS container agent. Usually, you run a cluster of EC2 container instances in an autoscaling group, but you still have to patch and upgrade the operating system and agents, monitor and secure the instances, and scale for optimal utilization. If you have a fleet of EC2 instances, managing fleets is hard work. Scaling the instance fleet can be a lot of work, depending on the size of your fleet. When you use Amazon EC2 instances to launch your containers, running one container is relatively easy, but running many containers isn't. This led to the launch of a new AWS service to handle this. Introducing AWS Fargate. AWS Fargate is a compute engine to run containers without having to manage servers or clusters. This removes the need to choose server types, decide when to scale your clusters, or optimize cluster packing. AWS Fargate removes the need for you to interact with or think about servers or clusters. Fargate lets you focus on designing and building your applications instead of managing the infrastructure that runs them. Container management tools can be broken down into 3 categories: compute, orchestration, and registry. Orchestration services manage when and where your containers run. AWS helps manage your containers and their deployments, so you don't have to worry about the underlying infrastructure. AWS container services that fall under the functionality of orchestration include Amazon Elastic Container Service. ECS is a highly scalable, high-performance container orchestration service that supports Docker containers and allows you to easily run and scale containerized applications on AWS. ECS eliminates the need for you to install and operate your own container orchestration software, manage and scale a cluster of virtual machines, or schedule containers on those virtual machines. With simple API calls, you can launch and stop Docker-enabled applications, query the complete state of your application, and access many familiar features such as IAM roles, security groups, load balancers, Amazon CloudWatch events, AWS CloudFormation templates, and AWS CloudTrail logs. Use cases for Amazon ECS include microservices, batch processing, application migration to the AWS cloud, and machine learning. The other orchestration service is based on the open source Kubernetes platform and is called Amazon Elastic Container Service for Kubernetes, or EKS. EKS is managed by AWS, making it easy to deploy, manage, secure, and scale containerized applications using Kubernetes on AWS. EKS runs the Kubernetes management infrastructure for you across multiple AWS availability zones to eliminate a single point of failure. Kubernetes manages clusters of Amazon EC2 compute instances and runs containers on those instances with processes for deployment, maintenance, and scaling. Not only does Kubernetes manage clusters of compute instances, it also schedules containers to run on the cluster-based available compute resources and the resource requirements of each container. Containers are run in logical groupings called pods, and you can run and scale one or many containers together as a pod. Use cases for EKS include microservices, hybrid container deployments, batch processing, and application migration. AWS offers flexible compute engines to power your containers. AWS compute engines for containers include Amazon Elastic Compute Cloud, or EC2. Containers run on EC2 virtual machine infrastructure with full control over configuration and scaling. AWS Fargate is a serverless compute engine for Amazon ECS that allows you to run containers in production at any scale. Fargate allows you to run containers without having to manage servers or clusters. You also no longer have to provision, configure, and scale clusters of virtual machines to run the containers. This removes the need to choose server types, decide when to scale your clusters, or optimize cluster packing. AWS provides Amazon Elastic Container Registry, or ECR, which is a fully managed Docker container registry that makes it easy for developers to store, manage, and deploy Docker container images. Amazon ECR is integrated with Amazon ECS, simplifying your development to production workflow. Amazon ECR eliminates the need to operate your own container repositories or worry about scaling the underlying infrastructure. ECR hosts your images in a highly available, secure, and scalable architecture, allowing you to reliably deploy containers for your applications. Integration with AWS IAM provides resource-level control of each repository. The steps to run a managed container on AWS are the following. You first choose your orchestration tool, which is either ECS or EKS. Then you choose your launch type, EC2 or Fargate. EC2 launch types allow you to have server-level, more granular control over the infrastructure that runs your container applications. With EC2 launch type, you can use Amazon ECS to manage a cluster of servers and schedule placement of containers on servers. ECS keeps track of all the CPU, memory, and other resources in your cluster, and also finds the best server for a container to run on based on your specified resource requirements. You are responsible for provisioning, patching, and scaling clusters of servers, what type of server to use, and which applications and how many containers to run in a cluster to optimize utilization, and when you should add or remove servers from a cluster. EC2 launch type provides a broader range of customization options, which might be required to support some specific applications or possible compliance and government requirements. AWS Fargate is a compute engine that can be used as a launch type that allows you to run containers without having to manage servers or clusters. As we discussed with Fargate, you no longer have to provision, configure, and scale the clusters of virtual machines to run containers. AWS Fargate uses an on-demand pricing model that charges per vCPU and per gigabyte of memory reserved per second with a 1-minute minimum. So let's summarize the primary benefits of AWS Fargate. It's serverless, so there's no infrastructure whatsoever to manage. Everything is managed at the container level. With Fargate, you can launch containers quickly and scale easily. And there's resource-based pricing, saving you a lot of money versus choosing other options. Docker is an operating system for containers. Docker users, on average, ship software 7 times more frequently than non-Docker users. It's an engine that enables any payload to be encapsulated as a lightweight and portable, self-sufficient container. Docker accelerates application delivery by standardizing environments and removing conflicts between language stacks and versions. Docker can be manipulated using standard operations and run consistently on virtually any hardware platform, making it easy to deploy, identify issues, and roll back for remediation. With Docker, you get a single object that can reliably run anywhere. Docker is widely adopted, so there's a robust ecosystem of tools and off-the-shelf applications that are ready to use with Docker. AWS supports both Docker open source and Docker commercial solutions. Running Docker on AWS provides developers and admins a highly scalable, low-cost way to build, ship, and run distributed applications at any scale. You can run Amazon ECS, Amazon EKS, AWS Fargate, Amazon ECR, and AWS Batch in Docker containers. You can use Docker containers as a core building block, creating modern applications and platforms. Docker makes it easy to build and run distributed microservices architectures, deploy your code with standardized continuous integration and delivery pipelines, and build highly scalable data processing systems. A Docker image is a read-only template that defines your container. The image contains the code that will run, including any definitions for any libraries and dependencies your code needs. A Docker container is an instantiated or running Docker image. Docker solves one of the main problems that system administrators and developers have faced for years. They ask the question, it was working on dev and QA, why isn't it working in the production environment? Well, The problem, most of the times, can be a version mismatch of some library or a few packages not being installed. This is where Docker steps in, or here comes Docker to save the day. In this example, there's 4 separate environments using the same Docker container. Docker encourages you to split your applications into their individual components, and ECS is optimized for this pattern. Tasks allow you to define a set of containers that you'd like to be placed together, or part of the same placement decision, their properties, and how they're linked. Tasks are a unit of work in ECS that provides grouping of related containers and run the container instances together. Tasks include all the information that Amazon ECS needs to make the placement decision. To launch a single container, your task definition should only include one container definition. The way Docker solves the aforementioned problem is by making an image of an entire application with all its dependencies, allowing portability to whatever hardware is in your required target environment or server. In short, if the app worked on your local system, it should work anywhere in the world because you're shipping the entire thing. On this slide is a schematic of an Amazon ECS cluster. Before you can run Docker containers on Amazon ECS, you must create a task definition. You can define multiple containers and data volumes in a task definition. Tasks reference the container image from the Elastic Container Registry. The ECS agent pulls the image and starts the container, which is in the form of a task, or aka an instance. Amazon ECS allows you to run and maintain a specified number of instances of a task definition simultaneously in an Amazon ECS cluster. This is called a service, which are long-running collections of tasks. If any of your tasks should fail or stop for any reason, the Amazon ECS Service Scheduler launches another instance of your task definition to replace it and maintain the desired count of tasks in the service, depending on the scheduling strategy used. You can optionally run your service behind a load balancer. The load balancer distributes traffic across the tasks that are associated with the service. At the bottom of the orange rectangle on the right, there's a red rectangle surrounding the words that read Key Value Store. This refers to etcd, an open source distributed key value store whose job is to safely store critical data for distributed systems. Its primary data store is used to store configuration data, state, and metadata. Containers usually run on a cluster of several machines, so etcd makes it easy to store data across a cluster and watch for changes, allowing any node in a cluster to read and write data. etcd's watch functionality is used by containers to monitor changes to either the actual or the desired state of its system. If they are different, the container makes changes to reconcile the two states. How you architect your application on Amazon ECS depends on several factors, with the launch type you are using being a key differentiator. The image on the left represents Amazon ECS launched with an EC2 launch type. Let's look at that architecture versus ECS launched with the Fargate launch type that's shown in the image on the right. The ECS launch type consists of varying amounts of EC2 instances. Both launch types show scheduling and orchestration and a cluster manager and a placement engine that are both using ECS. Orchestration provides the following: configuration, scheduling, deployment, scaling, storage or volume mapping, secret management, high availability, and load balancing integration. The service scheduler is ideally suited for long-running stateless services and applications. The service scheduler ensures that the scheduling strategy you specify is followed and reschedules tasks when a task fails. For example, if the underlying infrastructure fails for some reason. Cluster management systems schedule work and manage the state of each cluster resource. A common example of developers interacting with a cluster management system is when you run a MapReduce job via Apache Hadoop or Apache Spark. Both of these systems typically manage a coordinated cluster of machines working together to perform a large task. When a task that uses the EC2 launch type is launched, Amazon ECS must determine where to place the task based on the requirements specified in the task definition, such as CPU and memory. Similarly, when you scale down the task count, Amazon ECS must determine which tasks to terminate. You can apply task placement strategies and constraints to customize how Amazon ECS places and terminates tasks. Task placement strategies and constraints are not supported for tasks using the Fargate launch type. By default, Fargate tasks are spread across availability zones. Moving on from this point in defining what you see in both these images will differ a lot. The Amazon ECS container agent, shown near the bottom of the EC2 launch type image, allows container instances to connect to your cluster. The Amazon ECS container agent is only supported on Amazon EC2 instances. Amazon ECS uses Docker images in task definitions to launch containers on Amazon EC2 instances in your clusters. A Docker agent is the containerized version of the host agent and are shown next to the ECS container agents. Amazon ECS Optimize AMIs, or Amazon Machine Images, are pre-configured with all the recommended instance specification requirements. Now, let's look at the image on the right, showing a diagram of using the AWS Fargate launch type. Amazon ECS and EKS supports Fargate technology. Thus, customers can choose AWS Fargate to launch their containers without having to provision or manage EC2 instances. AWS Fargate is the easiest way to launch and run containers on AWS. Customers who require greater control of their EC2 instances to support compliance and governance requirements or broader customization options can choose to use ECS without Fargate to launch the EC2 instances. Fargate is like EC2, but instead of giving you a virtual machine, you get a container. Fargate is a compute engine that allows you to use containers as a fundamental compute primitive without having to manage the underlying instances. AWS Fargate removes the need to choose server types, decide when to scale your clusters, or optimize packing. AWS Fargate removes the need for you to interact with or think about servers or clusters, whereas the EC2 launch type, all those tasks and more must be handled by you manually and continually. With the Fargate launch type, all you have to do is package your application in containers, specify the CPU and memory requirements, define networking and IAM policies, and launch the application. By using Amazon ECS, you reduce your compute footprint by 70%. For that reason, let's quickly review the difference between ECS and EKS for clarity. Both container services have container-level networking. They also both have deep integration with the AWS platform, but the feature similarities stop there. Amazon ECS uses the Amazon ECS CLI, making it easy to set up your local environment, and supports Docker Compose, an open source tool for defining and running multi-container applications. Amazon EKS has a scalable and highly available control plane that runs across multiple AWS availability zones. The Amazon EKS service automatically manages the availability and scalability of the Kubernetes API servers and the etcd persistence layer for each cluster. Amazon EKS runs the Kubernetes control plane across 3 availability zones in order to ensure high availability, and it automatically detects and replaces unhealthy masters. Amazon ECS allows you to define tasks through a declarative JSON template called a task definition. Within a task definition, you can specify 1 or more containers that are required for your task, including the Docker repository and image, memory and CPU requirements, shared data volumes, and how the containers are linked to each other. Task definition files also allow you to have version control over your application specification. Amazon EKS provisions and scales the Kubernetes control plane, including the API servers and backend persistence layer, across multiple availability zones for high availability and fault tolerance. Amazon EKS automatically detects and replaces unhealthy control plane nodes and provides patching for the control plane. Amazon ECS includes multiple scheduling strategies that place containers across your clusters based on your resource needs, for example, CPU or RAM, and availability requirements. Using the available scheduling strategies, you can schedule batch jobs, long-running applications and services, and daemon processes. Amazon EKS performs managed in-place cluster upgrades for both Kubernetes and Amazon EKS platform versions. There are 2 types of updates that you can apply to your Amazon EKS cluster: Kubernetes version updates and Amazon EKS platform version updates. Amazon ECS is integrated with elastic load balancing, allowing you to distribute traffic across your containers by using application load balancers or network load balancers. You specify the task definition and the load balancer to use, and Amazon ECS automatically adds and removes containers from the load balancer. Amazon EKS is fully compatible with Kubernetes community tools and supports popular Kubernetes add-ons. These include Core DNS to create a DNS service for your cluster, and both the Kubernetes dashboard web-based UI and the kubectl command line tool to access and manage your cluster on Amazon EKS. Amazon ECS is built on technology developed from many years of experience running highly scalable services. You can launch tens of thousands of Docker containers in seconds using Amazon ECS with no additional complexity. The Amazon EKS service automatically manages the availability and scalability of the Kubernetes API servers and the etcd persistence layer for each cluster. Amazon ECS provides monitoring capabilities for your containers and clusters through Amazon CloudWatch. You can monitor average and aggregate CPU and memory utilization of running tasks grouped by task definition, service, or cluster. You can also set CloudWatch alarms to alert you when your containers or clusters need to scale up or down. Amazon EKS runs upstream Kubernetes and is certified Kubernetes conformant, so applications managed by Amazon EKS are fully compatible with applications managed by any standard Kubernetes environment. Amazon ECS includes an integrated service discovery for your containerized services to discover and connect with each other. Previously, to ensure that services were able to discover and connect with each other, you had to configure and run your own service discovery system or connect every service to a load balancer. Now, you can enable service discovery for your containerized services with a simple selection in the ECS console, AWS CLI, or using the ECS API. Amazon ECS creates and manages a registry of service names using the Route 53 auto-naming API. Names are automatically mapped to a set of DNS records, so you can refer to services by an alias and have this alias automatically resolve to the service's endpoint at runtime. You can specify health check conditions in a service's task definition, and Amazon ECS will ensure that only healthy service endpoints are returned by a service lookup. ECR is a highly available and secure private container repository that makes it easy to store and manage your Docker container images, encrypting and compressing images at rest so they are fast to pull and secure. Amazon Elastic Container Registry is a fully managed Docker container registry that makes it easy for developers to store, manage, and deploy Docker container images. Amazon ECR eliminates the need to operate your own container repositories or worry about scaling the underlying infrastructure. Amazon ECR hosts your images in a highly available and scalable architecture, allowing you to reliably deploy containers for your application. There's deep integration with AWS Identity and Access Management to provide resource-level control for each repository and integrates natively with other AWS services. In the next section of video number 3, Cloud and Data Metamorphosis, I'll cover the following: the evolution of data analysis platform technologies, the benefits of serverless analytics, and an introduction to AWS Glue and Amazon Athena. See you there.